Hi, everybody. I hope everyone is doing well, but I'm sure a lot of us wish that we were back in a physical classroom, but it is what it is. So, I chose to do my presentation on the chemistry of water purification, and I specifically chose to do it on how this is done on an industrial level. So, yeah, let's begin. So, a couple quick facts before we begin. Only about 1% of the Earth's water is readily usable by humans. The rest is actually just salt water. And of course, we can't drink salt water. We have to carefully purify it. And there was a really good visualization that I found on the matter. And it says if all the world's water was shrunk to the size of 1 gallon, then the total amount of fresh water would only be about a third of a cup. And the total amount of readily usable water that we can actually straight up drink is only about 2 tablespoons. So a very, very small amount. The big main steps are what's called screening. There's sedimentation, there's precipitation, filtration, adsorption, not absorption, and disinfection. So the first step is probably the most basic step, and that's called screening. And this just does things like gets rid of large particles that are in the water, any litter, debris that might be found. Nothing super sciencey about this step. The next step in the process is called sedimentation. The water is allowed to sit still, and the sediment will fall to the bottom, and then you can actually filter out the top, and the sediment will remain in the bottom, leaving you with cleaner water. And there's a couple different ways that we can make this a more efficient process, and those ways are called coagulation and flocculation. We're only going to go over coagulation in this presentation, however. So, what is coagulation? It's basically when the particles are dissolved in the water. They form positively charged ions that can't stick together, they just kind of bounce off each other. And what coagulation does is it adds something to the water called a coagulant, and it causes the particles, those positively charged ions, to neutralize and they start to stick together. And you can see a visual representation of it right here in this chart. The coagulant is added, those red dots are the impurities, and the green stuff is the precipitate that starts to form into like a mass. And as it's falling, it starts collecting those impurities up, those red dots, and you can see it falling to the bottom, and the top is just filtered off. So let's talk about precipitation. And if you look at my very simplified chemical equation right here, you can see that A, which is the ion to be removed, is reacted with B, which is another added ion, and you end up with C, which is a precipitate, and that's what's filtered out in this process. So precipitation is the process of removing ions from the water, and there are two major classes of ions that are typically removed from water, those being calcium and magnesium, and they contribute to what's called water hardiness. There's iron and manganese ions, and what these tend to do is contribute to bacteria growth. So those definitely have to be removed. And when iron is being removed, the process of oxidation is used. Molecular oxygen can be used, or potassium permanganate is added. So if you actually look at this chemical equation down here, you can see the iron is reacting with the permanganate in the H2O. That's that right there. And what happens is iron 3 hydroxide is formed. And when enough of that starts to form, it creates almost like a lattice. And this is the precipitate. And because it's non-water soluble, it is actually filtered out. So earlier I mentioned water hardening. That's when calcium and magnesium are found in the water. Water softening is when you actually remove those ions. So I want to mention that hard water is not harmful. It just generally doesn't taste good. And what it can tend to do is actually cause calcium buildup around the edges of things like drains in your sink and in your shower. You just don't want it in your everyday water. When people are removing this, they generally add lime and soda ash to soften the water. And when lime is added, it dissolves and it gives us 3 aqueous ions, a calcium ion, and we have 2 hydroxide ions. And you can actually see that in this chemical equation that I posted right here. You know, you got the calcium, you got the 2 hydroxides. This magnesium hydroxide is insoluble, and that spectator ion, the calcium that we saw up here, it reacts. And it reacts with the carbonate ions to produce calcium carbonate, which is another insoluble compound, and that is later filtered out. So all this brings us close to the end. We're at the filtration stage. There's not really a whole lot to say about this stage. Basically, sometimes the particles are too small to actually settle. They just kind of float around, do their own thing. So what a lot of places use in industry is what's called gravity filtration. There's a nice little diagram right here. And so the water goes in. Those red dots are like the particulates that you don't want in the water. And it goes through a layer of sand, gravel, and then it gets to what's called the underdrain, and that's just a reservoir. There's an outlet here where the water comes out, and sometimes they'll put like activated charcoal in there. We'll go over that in just a second. That's pretty much it. So while we're on the topic of gravity filtration, I wanted to show you guys something that I find kind of cool. It's called the life straw. You've probably seen videos of it floating around on the internet, but let me move my face again. It's the same thing that we just saw. It's just kind of in reverse, because instead of using gravity, it uses suction, and it uses a fine mesh, and then it goes through iodine beads. And what those do is they kill the bacteria. The catch-22 is it kind of gives the water like a weird taste. This activated carbon, powdered activated carbon, and that kind of just like freshens the water, and then it's safe to drink. A lot of people take these when they go camping. I think it's a pretty cool invention. So all this brings us to basically the last step, and that's adsorption. Remember, it's not absorption, it's adsorption. And it's more of a physical reaction as opposed to a chemical reaction. The powdered activated carbon that I mentioned before is added to the final product of the water. If you look at like the structure of the powdered carbon, it's really rough. It's really like rigid, and things like to get caught up in there, and they literally will get trapped on the outer edges of this carbon. And again, it neutralizes the taste of the water. That's usually the final product. But some places do what's called disinfection, which is exactly what it sounds like. It's adding chemicals such as chlorine to the water to further disinfect it, get rid of anything that could not have been taken care of before. Because of byproducts that are normally produced by this step, it's usually skipped. They usually rely more on filtration and coagulation. But there are some cool ways that we can disinfect it that don't involve chemicals, such as UV light. There's electronic radiation, there's heat, and there's even sounds. So when I heard that scientists could use sounds to purify water, I did some digging, and turns out it's true. What scientists have shown is that you can expose a sample of water to high frequency, high amplitude sounds, and in layman's terms, what happens is the high frequencies will actually cause the molecules to break apart. Those spaces that are left over from the broken molecules will create bubbles. And when those bubbles collapse, if you actually look at the picture here, that's called cavitation. And at that moment, at that explosion, that's high pressure and high heat, which does in fact disinfect the water. This YouTube link, I'll post that in the forum. Really cool video. That's where I got these pictures from. So I'm super into camping, and if you've ever been camping before, then you understand that having access to clean water is critical. So I found an article that goes over some ways that you can filter your own water when you're basically in the middle of the woods. One way is to use wood with a tube as like your fine mesh filtration system. Another way is to make your own DIY gravity filter, kind of like what we saw before. There is a more modern approach, which is to use purification tablets, usually chlorine or iodine, and you drop it in the water for about 30 minutes and it disinfects the water for you. Boiling for 1 minute is also an option, 3 minutes if you're in high altitude. But at the end of the day, if you don't have access to any of these resources, it's always best to just drink the tainted water and not die of dehydration. So in the midst of my digging, I found something called the Solar Cube, and this is a portable, self-contained water filtration system. It uses solar and wind power. It can filter anywhere from 1,500 to 3,500 gallons of water in a single day. It helps people after the Kashmir earthquakes in Pakistan in 2005 find relief and access to clean water, and it runs off about 900 watts of power, which is roughly the same as, say, a waffle iron. So for the weight of a car and the power of a washing machine, this is a sustainable unit that can literally save lives. And thanks for watching my presentation. I hoped you guys learned something. I hope you guys are doing well, staying healthy, both mentally and physically. Remember to wash your hands, get some fresh air once in a while, stay home, and have a good rest of the semester.